Welcome back to my lecture number 45. We will continue with the rotating machines. So, we will talk about now rotating magnetic field. So, rotating magnetic field is required for rotational motions to create a torque. We have discussed how force is created. To recapitulate, how a magnetic energy and the co-energy together is responsible for this force and this torque. So, now we will talk about circular motion. So, therefore, rotational motions where you need to have a circular distributed winding, where there will be MMF. You have studied in magnetic circuits magnetomotive force, which is responsible for driving flux. So, MMF is a function of the current and the winding, and winding is distributed. So, therefore, this is called MMF, and MMF has a direct bearing with the distribution of the winding and the current flowing through them. So, this creates a rotating magnetic field, as if the magnets are rotated in a very fixed speed, even though the actual effect is, the actual thing which is happening is the current is distributed in the winding, and effect of current is so 3-phase current, and so it is distributed. It happens that it creates a magnetic field which travels means travels around, and it is a rotating magnetic field. We will see how it happens. So, so these are the things. So, you can have a single phase winding. The single phase winding means, suppose we have an armature. So, like you have a armature stator here, you can see this is the stator. So, in the stator you can have a single phase winding. How? So, you wind like this. So, you can have stator slots here. So, you put one conductor here, another conductor here. So, here the current goes in, here it comes out. So, what happens? So, the current is coming out. So, I upwards, so I downwards. So, downwards into the screen or paper. So, this is up, that means out of the screen. So, this creates, if you have this Ampere's law, so this will create flux patterns like this. So, this will be closed flux lines, you can see. So, this will be creating flux patterns like this. So, if it is a so this is in the stator. So, the flux patterns like this. So, these are the flux lines. So, as a result, this is north pole, this is south pole. But if it is an AC current, if this current I is some I max cos or sin omega t or AC current. So, this magnet fluctuates, sometimes it becomes north, sometimes it becomes north. So, it is called a pulsating magnetic field, pulsating. So, single phase windings, suppose you can have a 3-phase winding that means you can keep another winding here. So, here the current is dot, this is cross, similarly another winding here, it is dot and cross here, and these are 3-phase windings. So, this is phase R, this is phase Y, this is phase B. So, in the RY phase you put 3-phase currents IR, IY, IB and IY. So, this is like 3-phase currents I max cos omega t and IB is equal to I max cos omega t minus twice pi by 3, that is phase difference is 120 degree, and here it is I m cos omega t plus twice pi by 3. If you see the phasor, this is IR phasor, this is IY phasor, this is IB phasor. So, that means they are 120 degree apart. So, each of them, so like this winding. So, let me change the color for the sake of your understanding. So, each of the winding, for example, this winding, so this winding for example, so this is IY phase. So, this will create a flux which is having this axis. So, then there will be IB phase here. So, this will be creating flux in this axis. So, all of them the resultant flux will be something. So, that is what we are going to see. So, the single phase AC magnetic, the AC current produces pulsating magnetic field, it will not rotate, it will have a pulsation. So, even though you distribute it across the stator, it will not rotate. So, what you want to do? So, you have to, so that way, so it cannot create a torque, you cannot create a torque here, torque creation is not possible, torque cannot, because it is pulsating. So, if there is a rotor inside, it will only, if the rotor, so it will just give torque pulsating force. So, pulsating force means, so pulsating magnetic field means pulsating force. So, no torque is possible. Therefore, this is not for generally it is not suitable for AC motors. Sometimes it is used, we will talk about later. So, therefore, we need a rotating magnetic field. That means how? That means the magnetic field, there will be a relative motion. So, that means as if a north pole, south pole, if this is a two pole case, it rotates around the periphery. So, that way we can achieve some rotating mechanical motion. Okay. So, let us do that. So, if you go to this, so again coming back to, if this is the current which is going into the conductor. So, you can see, I will just, this is the principle of physical principle of force, principle of force, how the force is created and which needs to convert into torque. So, you can see here the principle is, so this is in a magnetic field, suppose this is the magnetic field, that means this is the stator magnetic field, and if there is a current which is going in, so it will create, so this is an independent conductor. So, this is a external field, this is external field, and this is a conductor carrying some current. So, this is a conductor carrying current, this current can be induced or it can be sourced, that means you can put a source. So, in case of induction motor, this current is induced. So, if this is the current which is going in, so these are the magnetic lines of force, as you can see. Let me use a red pen now. So, these are the magnetic lines of force. So, what will happen in these cases, they will oppose, that means the field becomes weaker, these cases it becomes stronger. So, there will be, so it will always go towards the weaker field to minimize the storage energy. So, weaker field, so it will move, the force will be in this direction, because this side the field becomes strong, this side weak. So, as a result of potential balance, this conductor will be pushed here, and just opposite, if the, this is current coming out of the paper, this is dot means coming out, cross means going in. So, in this case, if you plot the lines of force, so it will be opposite. So, if it is opposite this side, so this will be the lines of force. So, this side the field becomes stronger, this side, so it will move like this. So, that gives you the right hand rule, CFM, current field motion, CFM. So, here C current field motion. So, motion CFM, CFM, C is here, field is here, so like this. So, CFM, the current field motion. So, you can see how it is done. So, but this force, these two ends of the coil should be in such a way that it creates a rotating sensation. That means, the field has to be essentially constant. So, this has one angle. So, if you put these two coils, two conductors in this, so this is the dot, this is the cross, and there is a field, this is the magnetic constant field here. So, this will go in this direction and this will go in this direction. So, there will be a torque produced. So, essentially the three phase rotating magnetic field has to be constant as much as possible, and it should rotate. So, when it rotates, there will be torque produced constantly. So, therefore, so this is achieved using a three phase supply. This is not achieved by single phase supply, as I discussed earlier. Here it is achieved by a three phase supply, not a single phase supply. So, we will see how it will be done. So, this is done by two kinds of windings. One is you can have a three phase winding which is concentrated, that means like concentrated winding. So, here is the, so you will concentrate, the winding is just here, here. So, this is concentrated winding, or it can be a distributed winding, that means the winding is everywhere. So, look at this. So, this concentrated winding, it is like two poles, it will create two poles which will not be perfectly smooth, because this side will be north. So, this will be north pole, this will be south pole. So, if you excite with a DC, the spatial distribution will not be, it will be rectangular. That means if your winding is like this and you are putting all the coils like this here and here. So, here suppose it goes up and here down. So, you know there will be the lines of force. So, you put a, so this is your magnetic core, so stator core. So, you know, so the flux will be like this, this will be a flux path. So, if you measure the flux density around the periphery starting from 0 here, if you keep on going with theta and here it is pi, I again come back with twice pi. If you plot this magnetic flux density, this is theta versus B, so it will be maximum. So, then it will come down. For example, this will be maximum for some time. Okay, so it will come down. So, it will become here, come down. So, again become minimum here, again like this. So, what will happen? This will be rectangular. So, the pulse produces rectangular non-sinusoidal. So, it will not be a sinusoidal thing. But if you have a distributed windings everywhere and the current is distributed, you can have a near sinusoidal MMF wave or flux wave. Flux and MMF are same, because you know, because this MMF by reluctance is the flux. So, reluctance is due to air gap. So, if the MMF is sinusoidal, flux will be sinusoidal. So, this is flux, and flux density is flux by area. Okay. So, therefore, the flux density to be sinusoidal, you need to have a distributed winding. Why sinusoidal? If there is sinusoidal, we can produce sinusoidal voltage and torque will be very uniform. That is the whole idea of becoming sinusoidal. So, getting into this, so you can see there are two windings here. This is a distributed winding, this is a concentrated winding. So, here the flux is not sinusoidal. Here, because of the distributed winding, the flux gets added up and it becomes sinusoidal. You can see here, this is a distributed winding. So, each winding gives you a rectangular flux, you can see this side. So, this is this winding 1, then coil 2, this is coil 2, this is coil 3, they are winding like this, coil 4 like that. So, each coil will produce a rectangular pulse. For example, this one will produce a rectangular pulse. So, each one of them if you add up, so this approximates sinusoidal, not exactly sinusoidal, but stepped. You can put more coils here, so it will approximate more sinusoidal. So, therefore, you can say that this flux is sinusoidal. So, this is called the this nature of the distributed winding. So, this is distributed winding. So, this distribution has certain tricks, it is beyond the scope of the work. That means, you should have a spread, proper spread, how the winding is distributed. So, these are all the winding techniques. It is called armature winding techniques. There are different kinds of armature windings. So, these armature windings are responsible for making the flux wave smooth or MMF smooth, not stepped. So, this is the whole idea of smooth. If it is smooth, the motor torque will be the smooth, because flux will be smooth. If the flux is smooth, flux interaction with the current, it will be smooth. So, torque will be smooth. So, that is what is the idea of making the winding distributed. So, smoother air gap flux, that is what, and therefore, lower harmonics, that means there is no, that means if there is a rectangular wave, you can decompose rectangular wave into sinusoid and higher order harmonics. So, there will be no losses, because if it is smooth, the frequency of oscillation is small, therefore, there will be no losses. If it is not smooth, there will be losses in the teeth, iron core, etc. And obviously, because there will be smooth torque, there will be no vibration or no noise. Efficiency is better and there will be better torque speed characteristics. This we will see later on. That means, there will be smooth torque speed characteristics. So, this is the whole idea of a distributed winding. So, therefore, we will avoid the rectangular winding or the concentrated winding. So, if you look at this, I have just told, this is a distributed winding. So, it is distributed everywhere. So, we will just have one phase, phase A and phase B. Phase A positive terminal coming out, going in. So, this phase A creates a wave for MMF wave like this. Similarly, phase B will create another MMF wave which is distributed. You can, phase B is 120 degree apart. This is phase A axis, this is axis of phase A, this is axis of phase B. So, this axis of phase B is 120 degree apart, you can see. Similarly, axis of phase C will be 120 degree apart. So, phase B and this is phase C. So, each one of them is 120 degree apart. So, you can say this is phase B, phase A. So, phase B will be here. So, they are 120. It is not proper diagram. You can say this is dot 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 here, this is cross. So, it is not properly done. So, this MMF wave will also be distributed by 120 degree apart. That means, if you pass same current, you find this current, a DC current here, the MMF wave around the periphery with angle theta, it looks like this. Similarly, if you do here, it will be displaced by 120 degree somewhere here, and if you look here, it will be displaced by 120 degree. So, that means, by spatially distributed winding, distributed and displaced with respect to angle theta, we can create MMF or flux waves, wave in the sense with respect to theta, that is the wave I am saying, which are 120 degree apart. That means, in space they are having a phase lag, spatial phase lag, space phase, not the time phase, is plus twice pi by 3 or minus twice pi by 3. So, MMF wave, suppose phase A MMF wave, if we can write say MMF of phase A, if cos theta, then MMF of phase B will be cos theta minus twice pi by 3, and MMF of phase A, B and MMF of phase C will be proportional to cos theta plus twice pi by 3. So, this multiplied by a constant is proportional to number of turns and current. So, this is Ni cos theta minus twice pi by 3. So, that means, MMF is partially distributed. This is the result of a distributed winding. So, let us now assume that this is a distributed winding. Assume this is assumption, assume that it is a distributed winding. In that case, and you can say neglect harmonics, that means, assume neglect harmonics, which is basically because of spatial distribution. So, we can say that assume that the MMF is sinusoidal. So, we call it only the fundamental component. That means, if you do Fourier series, there will be a fundamental component and there are harmonics. We neglect them. So, we will get a fundamental which is is sinusoidal like this. So, this is the, on the stator surface you get a flux pattern, MMF pattern, or the flux pattern like this around the twice pi. So, this is actually a complete rotation, it is developed, it is going from 0 to twice pi, starting from here to here. You go back 0, again come back 0, this is pi by 2, this is twice pi, this is 3 pi by 2, and this is twice pi. So, it goes like this and comes back like this. So, this is the sinusoidal nature of the MMF, and MMF by reluctance, which is primarily because of the air gap, is the flux. So, flux wave is sinusoidal, and it is rotor is experiencing this flux wave. So, rotor conductors will experience this flux wave. So, if the rotor has a distributed winding or rotor has a distributed current, it will interact with the flux to create a force, and because their force will be opposite in nature each other. So, it will create a torque. So, this interaction of rotor current and the stator MMF. So, interaction rotor current and stator MMF or flux results in force and torque, and this leads to rotation. So, this is the principle of operation, you can say, all right. So, we will see, but this is a single phase winding, all the time it will pulsate as I said. So, it will, the resultant torque force will be 0, so no torque. But had it been some other kind of winding called rotating magnetic field, so how do we do it? So, there will be 3 identical windings, they are spatially displaced by 120 degree, that is a 3 phase winding, I told you already. So, now, so how you can find out? So, one phase current is Ia sin omega t or cos omega t, second phase current is Im, third phase is this, and the corresponding MMF will be number of turns into Im. So, you can say the MMF is proportional to the current. So, MMF will be proportional to current, also space, because of distribution of winding. So, MMF is proportional to this current in time, at the same time it has a cosine theta component, because there is a, so MMF is some function of current into cosine of the angle theta, that is for phase A, MMF phase A. Similarly, MMF phase B, phase C. So, you can see this MMF phase A. Phase A is cos theta and proportional to current, and current is proportional to Im and the sin omega t. All of them are Im. So, it will be phase A MMF will be a function of theta and t. So, this sort of thing is called, it is partially pulsate varying, also time varying. So, this is a standing wave which is changing. So, there will be a, that means around the periphery you observe at one point you will find the MMF is changing with time, and at a particular time if you take a snapshot, MMF is also changing with space. So, this is spatio-temporal variation, okay, because of a sinusoidal supply and sinusoidally distributed winding. Remember, this is because of a sinusoidal supply. So, there one is sinusoidal, the number one is sinusoidal supply current and sinusoidally distributed winding. So, current or supply to be sinusoidal. So, this is the case of phase A. Similarly, what will happen to phase B? So, if you go to phase B, so this will become, this is lagging by 120 and spatial also lagging by 120. Phase C leading by 120 or lagging by 240, same thing. So, this is the 3 MMFs. So, to find out the total MMF at one time and space, you just have to add them. That means, at resultant MMF for a linear circuit, they are linear, no saturation, linear circuit, no saturation. So, all the MMF will be added. So, how they will be added? So, just add them. If you add them up, all of them, so what will be the resultant? You keep on adding them. So, if you add them, so you can see this is how rotating magnetic field is created. We will see the video. So, you add them FA, FB, FC, that means you add this one with this one and this one. What will happen? You will find that it become a very nice, we will see how it is, we will derive. So, if you add them, so if you add them, what will happen? So, let us add them. So, that means Fm is same, so you have to add, you can say sin cos theta sin theta plus cos theta minus twice pi by 3 into sin theta minus twice pi by 3, then plus cos theta plus twice pi by 3 into sin theta plus twice pi by 3. So, you can easily make a, you can just expand this and expand this. So, common Fm. So, eventually it will find 3 by 2 into Fm. This is what you will get. You please check it out. Okay. That means, this resultant MMF is a constant. It is not changing. It is rotating with, this resultant MMF at one point. So, it will become into cos omega t minus theta. This is the final. So, you will find this particular expression, that means this resultant MMF, F total or F resultant will become some F dash, some constant Fk you can write, into cos omega t minus theta, which is same as cosine function cos theta minus omega t. So, what is this wave for this? this is called a travelling wave. That means with theta, that means if you make a something like this at time t is equal to 0, and if you write theta here, so time t is equal to 0, this becomes cos theta. So this is 0 twice pi. So you can see this will become, so let me plot it somewhere here. So theta with respect to theta time t is equal to 0, this becomes fk cos theta cos omega t. So sorry, cos theta, so you will find this will become this is 0 to twice pi. Again it will repeat, this is at t is equal to 0. If you take t is equal to some, let us say some t1, this will become, this will just displace, this whole thing will displace. I will use a different pen color. So at t is equal to t1, so this will become cos omega t minus t1, sorry, omega t1 minus theta, or cos theta minus omega t1. So some constant, so it will be displaced by a constant amount. So it will keep on displacing, so this will travel. What will be the speed of rotation or travel is omega. So at omega rotation, so this particular thing is going to travel around the periphery. So this becomes a rotating magnetic field, or it is called a propagating wave or travelling wave. You can say it is a rotating wave. So I will write it as a rotating wave, and the speed is constant omega rotational speed, and the magnitude also 3/2 Fm. Please check it out. This is what. So this is called the principle of rotating magnetic field. So we will see how it happens because of the distributed winding. So if this is rotating magnetic field, you can imagine how does it happen. You can imagine that north pole, south pole, even though as if they are rotated at a speed omega, but actually it is not rotated, it is happening because of the spatial distribution of the winding, and the supply to them is 3-phase balance supply. So this creates a magnetic field north south pole as if it is rotating. If it is a 2 pole, north and south pole rotates. So that means if the magnets are rotating, what happens to the rotor? If the rotor is having conductors, it will cut the conductors. In the rotor, there will be change in the lambda flux linkages. So there will be voltage induced in the rotor or not? There will be voltage induced because this flux is cutting. So if this is cutting the rotor, just like cutting the conductors, there will be flux linkages cutting. So there will be voltage induced, and the rotor will have a circuit. So it will make a current to flow, and this current interacting with this field, there will be torque, and that is the whole principle of the induction motor. That is the whole principle of induction motor.